Given an assorted integer array R of size n and a number k, your task is to find the first k missing positive numbers from the array. If there are less than k missing positive numbers in the array, then add the remaining missing numbers by adding the values after the last value of the array until we have k missing positive numbers. Ignore all negative numbers. We have these examples here. So we have these numbers and we have a k of 4. So the first four missing positive numbers are 1, 4, 6, and 7. So we see that the highest value here is 8. So let me see what's going on here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So that is interesting. And then in this case, the first three missing positive numbers are 1, 3, and 6. So you have these go up to 5. Okay. So ideally, only 1 and 3 are missing, but they want 3 values, so we add 6 at the end after 5. In this case, we don't have to add anything after 8. Between 8 and 1, we have 1, 4, 6, and 7, so that we're good there. And here, 5. So between 1 and 6, we just have only 2 and 3. However, we need 5 things, so we just add 7, 8, 9 right after at the end. Here, it goes up to 10. We go to -8, -5. Then from 0 up until 10, we have 3, 7, 8, and 9, but it's less than 6, so we add 11 and 12 at the end. Okay, that seems not too bad. Let's look at the code. So again, it's a cyclic sort pattern, and here there are 3 phases. So this phase 1, phase 2, and then phase 3. So in phase 1, we do the traditional cyclic sort we've been doing in the video up until now. And the range starts from 1, not 0. Sort the numbers of cyclic sort, moving the cursor through the list. Okay. Check if it belongs in a range. That is, if it's bigger than 0, it's a positive number, and it's less than whatever length of the array we have. And check whether it's at the wrong index. So if it belongs in a range and it's at the wrong index, then just swap it out, right? Otherwise, move the cursor forward by 1. And then we come down here where phase 2, where we get the first missing positive integers within the current range. So we loop up until the array.length, and if it's less than k, if the number of missing numbers in this array is less than k, we are pushing it in there if it's a missing number. And what are we doing with extra numbers here? So it's a set, we're adding the set of what's at x, so what x is pointing to as an extra number. And then in phase 3, we're building up missing numbers until they are k numbers. So while the k missing numbers is less than k, we have fewer than k numbers there. We check a potential missing number by using the cursor. Cursor starts out at 1 plus the array length. Okay, so if we had an array length of whatever this is, right, this is 1 plus the array length. So it's like going to start from the value right after 10, for instance, 11. And then if the extra number isn't, if the potential missing number, right, in this case, 11 would be a potential missing number. If it's not inside extra numbers, so extra numbers we built by picking the values that are over here inside x. I think this is what's stepping through with the debugger. All right, so extra numbers is holding numbers that are in the wrong position, right? But again, they're within the range, so they're in the wrong position, which is why we're pushing the what's actually missing, right? But this is what's occupying the space, array index at x. Let's go into extra number, and we're making sure that, okay, the number is not already in the list. For instance, 10 is not already in the list, or 11 is not already in the list, because it would probably be one of those numbers that would be inside the array already, and then we're just pushing the potential missing number in there. And that's how we populate this end of the array, this right end of the array, right? So this populates the inner end of the array, the range up until the highest number you see there. And then this populates the one after. And that's it. Time complexity should still be O of n. While the space complexity, everything is happening in place. Although in place to some extent, right? Because this grows linearly with the difference between k and the array length. There's some relationship there. So it's like space complexity is a bit more complex. But I mean, you can probably approximate its budgets to be kind of linear in a way. So yeah, that's all there is for this problem. Again, I'm not even sure there's a LeetCode comparison to this. Hold on. So there's no LeetCode comparable to this problem, right? This is the closest thing I've seen. And it's very far away from it. So is the kth missing positive number? Like Facebook likes asking the question. I guess it's kind of similar because the kth one, right, is interesting. Okay. All right. So it's similar, only that in this case, I guess we would take the answer for this problem, right, and just return something indexed at k, whatever they put as k, right? We do the same thing, but still just return what's indexed at k. I would imagine that's what it is, and I wouldn't call it an easy problem by any stretch of the imagination, but let me see how they solve it. It looks like they're doing a binary search, which is very different from the tactic we're taking with this problem. We're doing cyclic sort, right? I would call it a modified cyclic sort pattern, akin to their modified binary search pattern. And so this solution doesn't like sit right with what we're trying to achieve with this series. So we can ignore it. See you in the next video. Cheers.